So I'm Arion. I don't mind how I pronounce it, really. It's in my seminar today. It's called Flight from the Ground Up, which I thought was quite a clever pun, because we're going to look at flight from the fundamentals and then go up and hopefully we'll be able to understand something about how it works. So I don't know how much aerodynamics or fluid mechanics you've done, so we'll give this a go and see what happens. So, fundamentals. Although sorry about the grads, PowerPoint made them all go italic, so it's just the way it is. So, start at the beginning. So, we've got an incompressible fluid here, which means density doesn't change. This is generally okay for most fluids that you're going to be actually flying through. So, we conserve mass and we get continuity, which basically says that the divergence of our velocity flow field is 0, and that's going to be quite important. Okay, that's a nice easy relation to work with. When we start to try and conserve momentum, it gets quite a lot more difficult, and we get the Navier-Stokes. So these are pretty intractable for anything that we really want to do in analysing wings or aeroplanes. It can only be applied on tiny scales and only then computationally. So we start by assuming things, and we're going to say, okay, the fluid's going to be inviscid, which means it's got 0 viscosity, which is the mu there, if you don't know. And we're going to ignore gravity because chances are it's air, it's not really heavy, it's supported and all that. So this equation here was actually derived before the Navier-Stokes, and it's called the Euler equation for inviscid flow. Okay. So now we're going to consider the assumptions we've made. So inviscid and incompressible. And if we think about them long enough, as Kelvin did, they imply another relation which is not immediately obvious. Imply that this here is true. Substantial derivative of circulation is 0. So chances are you probably haven't seen this before. Substantial derivative, which is big D over big T, is a time derivative in a flow field, used a lot in continuum mechanics. And it includes the effects of fluid moving in and out into the time derivative. You don't really need to know how it works. The most important thing is the gamma there, which is circulation. And you might be familiar with this from electromagnetics. There's a lot of crossover. Circulation, if we define a little closed curve like that there, it's the line integral of the flow field around that curve. So it tells us how much the fluid is sort of going around. If we make this contour smaller and smaller and smaller, we eventually get the curl. Well, okay, divide by area and we get the curl. Okay, so if we've got the derivative there, and if we assume an initial condition of no circulation, then circulation is going to be 0 for all time. Okay, so I've summarized Kelvin's theorem here. No matter where our fluid goes, if it ain't got rotation to start with, it's never going to get any. Okay, so chances are we can assume that this aeroplane is flying into a straight uniform flow which doesn't have any curl, and so curl of our vector field is going to be 0. Very good. I'll continue. So, back to Euler over there, slightly rearranged. Given that we've just showed that the fluid is irrotational, to describe that, irrotational we just say curl is 0, the same equivalent. We can have a nice little vector identity there, which I'm not going to prove, but it works. And so if we substitute that in and we assume steady state, which is time derivatives all go away, which is very happy, we get Bernoulli, and you should all be relatively familiar with that. So we have static pressure, P, and then dynamic pressure, which is related to the speed of the fluid, is going to be some constant all around the flow field. So if we look at these, we've got a pretty good description of our flow field, and we can try and get some results out of that. So this is a potential flow, which means we can introduce a velocity potential and the stream function. Sorry, I'm pointing one here, but that doesn't make any sense to you. Velocity potential and stream function. And if we define them like I've done down the bottom there, what happens is that the divergence criterion is automatically satisfied by the stream function definition, and the curl is automatically satisfied by the velocity potential. And if you consider the opposite criterion, so div u for velocity potential, the other way around, you get Laplace's equation for both, which is very nice, okay? It's very well understood, and most of you will know it from electromagnetics or somewhere else. So we can solve this quite easily. Now, if we were just being engineers and solving this, that would be enough. But given that you're physicists, we can introduce something which is slightly better and which will give us more results later. So, complex potential. If you note the equations we have up here, so that's effectively saying that derivative of velocity potential with respect to x is psi to the y, phi to the y is equal to negative psi to the x. Okay, those are the Cauchy-Riemann equations, which you may have been familiar with if you did complex analysis or something. So we can now introduce, a complex potential, which is, the complex potential is the velocity potential plus I times the stream function. Okay, and so grad squared W is 0. And after a bit of messing around, we can get quite a nice expression for velocity out of the potential. It's just the derivative with respect to z. That gives us the complex velocity, which gives us the components of our velocity field. So now, this is complex potential flow. Can we use it to understand why we get lift? Because of course, lift is quite a poorly understood phenomena by the general public. It's been understood by scientists for a long time. And most people generally have an idea that it relates to Bernoulli in some way. So fluid goes faster, less pressure. But most of the conventional explanations that you'll find are mostly wrong. So we'll start by trying to solve these equations for our flow. And generally the way we do this is by superposing lots of elementary flows. Okay, so what are these elementary flows? Uniform flow. Okay, complex potential U infinity, that's the free stream velocity, we say, times Z. Okay, not much to be said about that really. The source of the sink. This is when fluid is gushing out or gushing in to a point in your field. Now, of course, some of you will immediately say, well, this is breaking div u equals 0 because we've got stuff coming in. And that's very true, it is. But it's only breaking it at r equals 0, yeah, which is a singularity anyway. And we don't usually consider flow that's going so close to that this is going to be an issue. It's a point source. So we can treat it as being a solution to those. The irritation vortex is very similar, and maybe it requires a bit of explanation because there are a lot of vortices out there that we can model, but only one of them is irrotational, which is curl is 0. And this is the stream function defined, complex potential, I times gamma over 2 pi times ln z. Okay? This also breaks irrotationality at some point, at one point, and that being r equals 0, where there's a singularity. And for the same reasons, it doesn't really matter. We can consider the flow in all points except r equals 0, and we get a good idea of what's happening. Now, the other very interesting thing about this vortex is that in the definition of the parameter of the complex potential there, we have a parameter gamma, which is none other than the circulation parameter we saw earlier as that little line integral. And this, for any closed curve that goes round and encompasses the centre of the vortex, it has a circulation of gamma there. For any curve that doesn't enclose the centre of the vortex, it's got no circulation. But curl is still 0 for all points except r equals 0. These are the three purely elementary flows. Now we can make another quite an interesting flow by taking a source and a sink and then bringing them slowly closer together and making them stronger proportionally. Then we get, in the limit of that, we get the doublet or hydrodynamic dipole, which is basically the same as an electromagnetic dipole, except now you have curves of stream function and curves of velocity potential. This has got a very elegant complex potential. It's simply the inverse of the space there. By the way, Z, I probably should have explained, Z is x plus iy. So we're treating the complex potential as a mapping of this complex space as such. So now, we're going to look at trying to model a real flow as such. And the flow I've chosen is a cylinder which is spinning in a uniform flow. Now this might seem quite arbitrary to you, I mean, like maybe spinning baseballs and things, but how does this help us? Well, we'll get to that, and it turns out that the cylinder, spinning cylinder in particular, is actually going to be very, very useful when we want to try and look at how aerofoils behave. But now, I'll just sketch the solution to this. So what we have is a line flow. That's not my image, by the way, I got it. It is not copyright. Doublet in the center, and then on the doublet, to make it rotate, we put a vortex. Okay, this doesn't really show the decomposition of the thing, but that's what you get. And so, if we draw this flow and then look at it, we'll note that there's a closed streamline in the center. So your flow will look something like it's going to be curved a wee bit like that. But in the middle here is going to be a closed streamline, and then inside here there will be some mess. I don't actually know what happens. But the point is that a closed streamline means that this fluid is always rotating around here, or it might have zero velocity, some velocity, and no fluid outside this closed streamline ever goes through the streamline, because in these cases we treat streamlines as not being able to cross, so that causes trouble. And so nothing out inside, in the same way, can ever go outside. So this is essentially a solid body. We've added lots of little flows and things together, and we've got, that's good, cool. We've got a solid body in our fluid. And so now, the complex potential of this, if we just add up uniform flow, and then a doublet, and then a vortex, pretty simple, differentiate that, and we get the complex velocity profile down the bottom. Okay, now it gets a bit more tedious, not too difficult, but tedious. And so we want to use Bernoulli. And so from that we say, okay, if we want the static pressure distribution around this thing, which is going to be pushing on it, we want some constant, doesn't matter what it is, minus a half rho absolute U squared. So it's easier in this case to and we want to evaluate that at the radius of the cylinder here, which I've spelled A in the equation there, because that's going to give us the pressure distribution that is on this body, well, this sort of flow artifact body in the flow. So in polar coordinates, you substitute in, it looks quite a bit of a mess, it is a mess. So now if we want to consider if there's any lift on this thing, we say, okay, well, lift is going to be sort of by definition, there's not any really hard and fast definition of lift. It's going to be a force, perpendicular to our flow field. This is not actually always the case. You can often have lift which is generated in a slight sideways direction. But generally we're going to say, okay, perpendicular to the flow. So we can integrate this pressure distribution, therefore, over the whole cylinder and take the vertical component, so sine theta, integrate the mess. We find that all the odd powers of sine drop out because it's going from 0 to 2 pi. And we get a very, very interesting relation. And that is L prime, that's the lift per unit depth of this thing, which is obviously only a 2D flow, is going to be the density of the flow times the free stream velocity that we're putting in it, that's the velocity here, not the velocity inside there, times the circulation of the flow around the cylinder. This is called Kutta-Joukowski's theorem, the Kutta-Joukowski theorem. Kutta being, of course, grunge Kutta fame. Should all have heard of that. And so this is a very useful relation, and it can give us an understanding of why this lift is actually occurring. Because it's not due to sort of just a linear Bernoulli thing. So the velocity, a common explanation is that the velocity over the top of the wing is faster because the the fluid is being forced to equal transit. That's it.
Because the sun goes and they have to go reach.
Yeah, and it's not right. But this is saying, well, wait a minute, there's circulation in there. Okay, so for some odd reason we have circulation churn. And now this arm, we've done this for a spinning cylinder, can be generalized to any body artifact in a flow field that has circulation. So now we say, we're very close to modelling the flow over an aerofoil, American, British, whatever. So here's a little pressure distribution, and I'll show you sort of where this comes from. It turns out that, as I said earlier, spinning cylinders are very, very important, because if we know the flow of a spinning cylinder, there are some conformal transforms, I've got one up there, which can make this spinning cylinder flow into an aerofoil flow. And that's very, very useful. We see if we have this cylinder up here, the centre is offset slightly from the origin. That controls the shape of this aerofoil. Then we transform it there by what's called the Jacuzzi Transform. Okay, relatively simple. And we get flow over this complex aerofoil shape. Okay, this is not only useful for working out pressure distributions and flow distributions, but it's also a very nice way to define aerofoils. So before Navier Series 6, they were defining aerofoils mostly parametrically, which was rather difficult, and it's very difficult to model those flows if you've got fluid over them and you're trying to use potential flow. Then they said, okay, well, why don't we do a conformal transform? And there are a few conformal transforms that are more complex than that, but can give better representations of aerofoils. And so they use that to define the aerofoil shapes. So, applied complex analysis, now you know. Now, if you've been paying attention, of course I said that this is a spinning cylinder, and currently we haven't defined the circulation. So, using a Jacuzzi transform, for different values of circulation, we could get the top pattern over there, or we could get the bottom pattern. Of course, the top pattern is not a steady state flow in real life. So generally what we say is we define the Kutta condition, which is another sort of boundary condition. That says that the stagnation point of a flow over an aerofoil will always be forced to the rear edge, so the edge here. Now, stagnation point, that's, if you look just to the right of the X there, there's a point at which the fluid appears to be coming straight out of the aerofoil. It's not actually passing through that. It's sort of, that's, if you imagine this thing flowing in reverse, that's the point at which fluid goes in and then stops straight on the aerofoil. It's sort of an artifact of potential flow because, of course, the fluid never really stops. I'll show you hopefully a CFD later. And so this is effectively adding in the effects of viscosity that we neglected all the way at the beginning when we said that Navier-Stokes was too hard. So this is sort of a cheap way to add Navier-Stokes back in again and get good results. And so now, using all that we've learnt, conformal transforms and the complex potential, we can get a classical result, which is very elegant. For any Jacuzzi aerofoil here, the coefficient of lift, we define that as the lift force divided by dynamic pressure, in a way that makes it dimensionless. Lift force times area divided by dynamic pressure. And we get a very good agreement with real life. So this is 2 pi sine alpha. What's alpha, by the way? Alpha is the angle of attack of this aerofoil. So in the little Jacuzzi model I showed you earlier, aerofoil was straight. But in real life, planes don't always fly straight. So an angle of attack is usually defined, we take a point there, we take a point, this is our angle, alpha. And you'll see that the angle alpha, of course, makes lift larger until a certain point here. But that's when funny things start to happen. But if you note, even with this very simple potential flow model we have here, using just standard Bernoulli, no viscosity or anything, we can obtain some very good results down up to, say, angle of attack about 10 degrees. Okay, this is a Navier-0012 aerofoil. Some aerofoils do behave differently, and we need to model them very differently. So now, we can go back to our Kutta-Joukowski relation, which is this, just as a reminder. That there. And say, okay, well, why lift? Okay, Benedict has just told about equal transit theory, which is basically saying, well, the air at the top has got to take the same time as the air at the bottom, and so it's going to be going faster, and so you're going to get lift. That's not the case. Looking at Joukowski there, Kutta-Joukowski, we see circulation, and that should tell us that the lift there is actually a result of the flow being turned or being curved. This is not something you think about when you think of aerofoils. It's like, well, flow is just speeding up. But it's primarily the result of turning the flow that we get lift. You can think of this, curved streamlines over the top there, they induce a low pressure on the top of the aerofoil. And the streamlines which are sort of curving to avoid the front edge there and go under, they induce a high pressure, the red, down at the bottom there. And so this is leading to a net force upwards. It's also leading to a net moment in the aerofoil. So this thing's being twisted, and that has a lot of applications if you're trying to work out when your wing's going to break off, okay? This modelling is very important there.
So it's a result of the flow being curved then.
Yeah.
What would happen if you were to curve the bottom of your aerofoil? Like, as well?
In what way? Do you mean,
like
I can show you. Do you mean something like, if we have an aerofoil like that?
Like that or like the other way as well.
Concave on the bottom.
Yeah.
Like that?
Yeah.
Yeah, there are a lot of aerofoils like that. And so, for an aerofoil like this, symmetric aerofoil, that generates no lift at zero angle of attack. So if you're flying this thing straight, just slightly elliptical, into the fluid stream, you're going to get no lift. For these aerofoils, you're going to have to take it at an angle of attack. Of course, the reason why planes can fly straight is that they have them curved upwards. They don't have aerofoils facing straight in. So they can use symmetric aerofoils. For the curved ones like this, you can get a whole lot of very weird aerofoil shapes. But that's one of them. And it does work, and it usually works even, so this aerofoil here works, I've got a CFD later, works even for a very low angle of attack. So that's about, I think it's at 1 degree or so. So these ones, it still works. It can work for 2 reasons. One possible reason is that if you're going fast enough, this forms a little vortex sheet inside here, and this actually becomes a larger aerofoil. That only happens when you're going fast. Otherwise, the effect of the flow is still such that this is curving, there's a net curve down there and a net curve. Though this is of course being curved upwards slightly here, and that would imply a greater pressure on here. It's actually being curved down overall. So these aerofoils might not be more efficient, but they're generally better at, say, high angle of attack and things like that. So it's a trade-off.
So does the Wright brothers or anything
Did they know any of the science, or were they just pretty
No, they didn't really. The mathematics, so like the Euler equations were obviously formulated by Euler, so they were known quite a while before. And the spinning cylinder thing, so spinning cylinder induces lift, that was known before as well. But they didn't have potential flow to model the things. So they had a very similar aerofoil to this. It was quite long and thin and prone to breaking, unfortunately. And they just worked it out and flew for a short time. Any more questions on that? Oh, cool. So I said I'd address this, because all physicists like xkcd. So why can planes fly upside down? This sort of comes back to the discussion we were having about that. Just giving myself some space. So we can sort of recast this question and say, how can we generate negative lift from an aerofoil? Okay? Because if we can generate negative lift from some aerofoil, if we turn it upside down, it's going to pull our plane upwards. Okay? So I've already shown you, you could think of this mathematically, that we have lift, oh no, I'll write this in terms of constant coefficient, which implies that if we take alpha negative, we'll get negative lift. So this works for symmetric aerofoils. If you just have, like the middle one there, NACA 0009, and you take it into a negative angle of attack, you get negative lift. And that should be kind of obvious, because given that an aerofoil like this is symmetric, turning it down is the same as turning it up. It has no shape difference. Now, for a different aerofoil here, NACA 2408, it behaves slightly differently, because this one is curved. It looks more, well, like the aerofoil we had some time over there. It looks more like that. And so this aerofoil will work and give you upwards lift even if you tilt it down a bit. Of course, it only doesn't give you a lot of lift, and you can only go so far. And if you take this thing down far enough, it's going to give you negative lift. Now this is quite interesting, because this also shows why if your target policy is wrong, because you think, okay, turn the aerofoil upside down, we've got this weird banana shape like this. I'll draw that better. Okay, and you might say, oh well, now what is happening? They're sort of both being compressed. Which fluid side travels faster, if any? But if it's at a high enough angle of attack, the net curvature downwards of the flow stream, well, net curvature of the flow stream is going to be downwards. Okay, and that's related to circulation, of course. This thing is traveling at a free stream velocity, u infinity, and then after aerofoil, it's curved. That's related to the circulation, and so that's how you get lift. And thought of something like that. What was it? No, it might come back. And so that's how you get planes to fly upside down. You just have to tilt them high enough. That's what I remembered. An interesting example of an aerofoil is the flat plate. You don't have to actually have any curves. If you've got a plate there and you tilt it up like this and you fly it forward, you'll get some lift. It's not great, of course, but that's primarily circulation. No, sorry, it's solely circulation. Okay? If you get circulation, you get flow. Now, that was nearly the end, but as I've got 5 minutes or so, I think I'll talk a bit further. Real aerofoils work to a point, and then they don't. So if you see, we've got this nice line, which is pretty much what we predicted. Then after 18 degrees, we drop, and then if this plot was extended, we'll be down here, okay? They just drop off. Why does this happen? It's called stall, okay? And it's a result of potential flow, which we've just been talking about, going wrong, because we now can't neglect anything. So this is a nice CFD. There you can see the stagnation point at the back in blue. You can also note that, of course, it's not really zero velocity, because this is solved using a turbulent K-epsilon model, which is like that, but much more complicated, and it gives a reasonable idea, reasonable modelling of flows around aerofoils. So this is all functioning normally. You can get some lift. You can see the top red area there is where the fluid's going very fast. If we tilt this thing backwards, we get this, which is really bad. So this is not a very high angle of attack visually. You would think, oh well, obviously if we're going to have our aerofoil up like this, it's going to be pretty bad. But even at that angle, which I think I'll put as 30 degrees, you see that this thing just blows up. And instead of having nice smooth flow, this thing's just blasting its way through. Okay, that's a result of boundary layers, which is something which I haven't covered at all, but it's a very interesting area. And the whole point is that the boundary layer of the flow at the top of the aerofoil is now, as a result of going too fast, it's just being blown off. And so the fluid doesn't actually stick to the aerofoil as such anymore, it just goes. So you might say, well, given we've got all these CFDs, why do we need potential flow anymore? Because obviously using this we can predict stall and we can predict everything, we can get nice lift curves, because that little curve there in blue is the CFD lift results. The black dots are blue dots, our experiment. But CFD has a lot of issues, and one of its most important issues is that it's not really good for multiphysics. So if you want to say, okay, we've got this lift distribution on our aerofoil, now we're going to make this aerofoil out of plastic, so it's sort of got some nonlinear viscoelasticity. How are these things going to interact? Okay, it's very difficult, very computationally intensive. So theoretical aerodynamics, like this potential flow, is still in use for those kind of things. It's not like we can just CFD it. It's a very active area of research. And lastly, we had, you saw the stall there. Stall is pretty bad for an airfoil. Okay, you don't get any lift out of it. But if you have a superjet, or if you have some nice control systems, you can do things after stall. So it's called post-stall maneuvering. So this is one of the first post-stall maneuver to be completed without loss of life. And what happens is, you note, plane goes up like that. This is about the stall point there, it's pointing up, but instead of being sensible and dropping his nose, the pilot is just going to ram this thing back. And eventually, he reaches an angle of attack which is backwards. Okay? And so this is quite bad. If you were to try this for, say, like a Supermarine Spitfire or something, either you would drop back into an uncontrollable stall, or your wings would break off and you'd drop into an uncontrollable stall. It's really, really not good. So, the initial research into this topic was quite dangerous, as you might expect. But if you've got strong enough wings, and especially if you've got triangular wings, what will happen? If you've got this triangle here, this is your fighter jet, you can often rely on aerodynamics to bring you back into sort of more suitable areas over there. Because if you've got this flow hitting here, which is now causing an immense amount of drag, this thing is going to exert a moment on your, say your centre of mass is here, centre of lift is here, well, or centre of drag, and it's going to tilt you. Okay, you can do it that way. It is more dangerous. So a lot of research by certain large air forces around the world has gone into designing what they call advanced control surfaces for working out this thing. So of course you've all heard of probably plasma airfoils and things. That's still a very theoretical area of research. But you can have lots of interesting control mechanisms on your tail. So we call them stabilators, and the reason we call them stabilators is that they can make you stable after doing the same things like pulling plane back. So that is, that's called the Pugachev Cobra. If you want to look it up, there might be some videos or something.
What's the actual use for that maneuver then?
Yes, that's interesting. It's a sort of slightly. The main interest is, of course, air shows, and that's why. There have been some people who have said, oh well, it could be useful in this situation if you've got a plane behind you and you want to brake suddenly, because this drops a lot of speed and can drop height as well. That's not really useful, but there's another maneuver which is, well, this is, of course was the first post-stall maneuvering to actually be completed successfully. And there's another maneuver which is called the cool bit, and what happens is instead of trying to bring this out back inside there, what you do is you pull this thing back, and then in, say, a diameter of about maybe 5 plane lengths, you pull yourself into a tight loop. And so this thing's basically stalling the entire way round. And so that's a more useful combat maneuver because you can maintain speed with that. So you can go into a quick loop and you're effectively just dropping some time, staying in the same speed and staying in the same place. That's more useful, and there are other maneuvers after that which are not related to pulling your wings back, but also require post-stall technology. So, that's my talk. I hope you enjoyed it all. Do you have any questions? Any further questions?
We might flow as a 2D system. Aren't we going to get some 3D effects?
Yeah, I was thinking someone would ask that. Yes, for this little modelling, you usually end up doing. Okay, so I said lift per unit length back there. And so this predicts if we've got this aerofoil here, I say this is our plane, it's a bit thick, but it's a lot. So we're going to have a constant load on this thing. This doesn't actually work. What we end up having is a distribution which looks like this. And we can model that. You may have heard of it, maybe you're asking this question because you know something about it. It's called lifting line theory. And what we say is that as you get closer to the edge here, what happens is that you start shedding vortices in other directions. So what happens here, this thing's a vortex going around like this. That's sort of our spinning cylinder, if you imagine. But now it's going to be modelled into spinning vortices which look like that. And you can see that if you know, if you've seen a jet stream, that's some vortices which are being shed off as such and causing condensation, so you can see them. And so, yes, we can extend it, and we can extend this theory without resorting to understanding viscous effects. So Prandtl's lifting line theory, which is usually the way we model this, is a potential flow method. It just involves putting some more vortices in places. So yes, we can do that.
And how do the ends of the wings go up?
Yes, they're generally to prevent, we've got a wing flap like that. That's to prevent flow here, fast flow here. So if you imagine this thing's being curved, how will I draw it? This has got low pressure here. This has got high pressure. So if you lift your wings out like that, this usually just flows around there. And that is one of the reasons why we have these vortices being shed. If you have the little winglets, then you prevent that from happening. And so I'll be interested, I wouldn't know if this actually happens, you shouldn't see so much jet stream on a wingtip aircraft. I haven't actually observed that before. So that's what they do.
Are you a pilot?
Huh?
Are you a pilot?
No, I'm not a pilot.
When you get something like a modern jet fighter, something that's got a really high speed to it, when you've got your, can you go to the image?
Yes, sure.
Yeah, that one there.
Yeah.
So if you're going fast enough, can you essentially generate lift because your air is moving down like this, or is it like just there is no lift? It's just entirely on the thrust of the aircraft to propel it up?
Well, there's always some lift involved.
Yeah.
So if you're saying, like maybe you're thinking, we've got this flow, we're forcing it to go down like that. Is that going to cause some like thrust? Is that sort of what you're thinking of? Or?
No, it's kind of like
Good, George.
You have a force which is
Oh, just because I guess this one here, is that, so if you got your aerofoil, is that modelling from like the air coming in this direction?
Yeah.
What I was saying
it's
is,
straight.
yeah, is if you've got enough propulsion coming from down here, if your air is coming kind of like that way because you're going fast enough. Is that something that happens?
Yes, that is, we've modelled this at slow speeds, and so that is the case generally, and that's why we can have lifts which is not really perpendicular to your flow, because the flow is actually now being influenced by movement. That's generally what happens there. Is it's not good because what we have is we have what's called induced drag. So if we have this vector like this, this is the useful lift it's giving us is that, but it's also adding to the whole drag on the thing with this here. And so for like normal aerofoils, Wright brothers and things, that's not something you really need to consider. But if you're going very fast, it is. But then this only works for up to maybe Mach 0.5. When you go faster than that, everything falls apart again. And so supersonic aerofoils look like this. Okay, sharp. And the whole point there is to minimize shock waves. So once it does work like that, but you're prevented from getting sort of massively high things like that, simply because if you go that fast, you'll go supersonic anyway. And then it all breaks down. But we still have some models, but you can't really use potential flow.
So which of the potential flow sort of assumptions is violated under the supersonic?
Incompressibility is the main thing, which is kind of the worst assumption you can have violated, because like in viscid flows, we have some sort of semi-potential methods for viscous flows. You can understand them relatively well, but when you get supersonic, you now have compression and you have to modify your Navier-Stokes, which makes it very difficult. And continuity, that is one thing. Continuity, which normally says grad of u equals 0, that's true for inviscid flows, for non-Newtonian flows, for whatever you can think of, except compressible flows. So then you have what looks like that, sorry, plus rho t is 0. And so, where rho is the density, and so it becomes very difficult, and we get shock waves and things, which are very cool, but very hard to understand.
This is like a bit unrelated, but why when you break the sound barrier, why does it produce a boom? Because I don't actually know, I just know it does.
The boom is the shock wave, so okay. I will give myself some space. So the first thing, the easiest shock wave to consider is called a normal shock, which can occur just if you've got a duct, okay, a pipe, and you're sending some flow through it. And then if this flow is getting very, very fast to say like Mach 0.9 or something like that, and you have a microscopic perturbation inside there, what will happen, if this flow is going faster than the speed of sound, so it's Mach 2 or something, and you have a tiny perturbation here as it's slowing down, so as it's getting near to the Mach 1 limit, then it suddenly forms, boom, a shock wave there. And the reason that shock wave occurs is that it can't compress. You can compress this thing slowly. It's sort of possible if you were to have a very gentle kind of nozzle. Sorry, nozzles work slightly differently in supersonic flows. But generally, if you're being forced by a little perturbation, this thing suddenly just loses energy and increases entropy. And so the whole thing is that this here, the fluid at one side is not a lot of speed difference, but there's a lot of density difference. Well, actually that implies speed, but no mass flow difference, that's what I meant. And that's rho 1, density 1, and density 2. And so the sudden change in density causes a shock wave, and of course a sound wave is just a weak shock wave. So if you've got now a plane that's pointed nose, and you're getting, this is a normal shock, and then what you get is oblique shocks, which go like that. So that's why, if you're standing here, you'll only hear the sonic boom until the plane's over there. And so these occur for a similar reason if you've just got this thing in the nose, which is suddenly causing the air to go from a supersonic speed, well, okay, relative to this, to a sonic speed. And the shock wave, a shock wave is just sound, very loud sound. And so by the time it hits your ear, it's not really a shock wave anymore, it's just a loud boom. Does that make sense? Maybe?
So is it actually the waves catching up with each other? I don't think
Well,
I remember physics teachers talking about that somewhere.
Waves catching up.
Like if you're going just at the speed of sound, then your sound waves aren't like
Well, possibly, possibly I get
they'll
what you
join
mean.
up and
It's called, like, if any of you have done a lot of differential equations, like, you know, method of characteristics and stuff, how you have domain dependence, range of influence. It's just basically, these are defined by hyperbolic partial differential equations. So what you have is your observer here. Well, he won't be so happy when the shock hits him. And then this here is the propagation of information. So information can only propagate at the speed of sound, and this thing is going faster. So it's making a big shock wave here, and this shock wave will move along until it hits you at some distance. And so it's, if this guy inside the pilot here shouts, makes a loud sound noise, you might have had the familiar diagram which looks like this. So this is where his sound propagates to, because he's going faster than the speed of sound, so the only way sound can go is backwards, can't go any forward. Because, yeah, it's like, it's sort of like being redshifted far away so that it can't actually go forward anymore, it just goes backwards.
and if you're going at the speed of sound, then that one will be horizontal.
Yeah. Generally, of course, it's very difficult to go exactly, but you get a shot which looks very close, like that.
Is that the same as wake in a boat?
Not really. Wake is something which happens in aerofoils even at supersonic speeds. In fact, this is actually a really good example here, at least for this. No, go back to the next one. If we look, take the velocity at this point here, we see, okay, there's a bit of a faster velocity at the bottom here, and a reasonably fast velocity at the top here, and then in the middle, it's quite low due to this thing just sort of carving out a stream over there. So the wake is what? This is wake. You have wakes in aerofoils and in planes and in everything that moves through fluid. That's just saying if you put a body there, then unless you go infinitely far away, there's going to be some velocity deficit over there. So this is the free stream. Generally, we usually define the wake as being sort of 0.9 free stream. So that's your sort of wake length. And so that's,
There's a thing in boats called the Pyhssoc.
yeah, that's not a supersonic thing. That's, you don't all have to stay, by the way, if you don't want to listen. That's not a supersonic phenomenon, because obviously the speed of sound in water is like 1,000 meters a second. So no ship has ever gone that fast.
No.
And that's, Pyhssoc is sort of just a nautical term, which is, if, as far as I understand it, I'm not a sailor either, if you have, say, a wave or something, that thing, and you've got ship and water, you have some wave or perturbation, as this thing hits, it's just going to go up and exert a sort of an impact on that. So I don't think that is actually, it's definitely not a supersonic thing. So I think it's just that.
Thank you.
Cool, thanks for listening.
Cheers.